Hey, Georgia Tech Digital Media here. We're a group of graduate students doing a class project. This is Sarah, Miriam, and Jean. This is me, Chris, your narrator. I want to clarify, by the way, you're not going to see Sarah in a lot of the photos because for most of the photos, Sarah's the one behind the camera taking the pictures you're seeing. For our group project, we built a spectrometer. It's easier to say what a spectrometer does and what it produces than to say how it goes about it. It takes light that's been reflected off of material or gone through a thin material, and it can then divide up the wavelengths from it, so you can get kind of a fingerprint of chemicals in a liquid or for astronomy purposes. And now for scientific applications, a lot of research has gone into very specific material choices for the reflectors, into very careful design for getting spectrometry data off of objects of various scales, sizes, and distances. And these devices on the low end are in the tens of thousands of dollars. They're used in labs for identifying, say, blood doping or other purposes. On the high end, they might cost hundreds of thousands of dollars. Very complex machines, very expensive. And for astronomy purposes, you get a lot more than just a single spectra of data to work with. They've got to triangulate a bit. Now, there's all kinds of instructions on the web to build a spectrometer, and you might think that sounds crazy, but the spectrometers look like this. So this is the one Jean made. We wanted to start the project by building some of these instructions on the web. This is the one Miriam put together. This is Sarah's. This is mine, based on a cereal box with some tinfoil. And the results leave some to be desired. They're not very practical or scientific. There was a great Kickstarter, though, by the Public Labs group to generate a kit, a $40 spectrometer kit. We bought this kit, which you can use to submit data to their spectral workbench. Here's the kit once we did our unboxing with all the parts. It comes with instructions, and so of course, right off the bat, we're just sort of reading through the instructions. It comes with a supplement. There's a second page that clarifies some details. For starters, we cut off the edges of this cardboard thing and folded at the dotted lines. That's actually the part that has the slit on the front of it. See, we're fitting it here into the housing. We then snap the camera in half. You don't actually need both parts of it. The bottom part's just plastic. You can then snap the front of the camera off. And that's to expose the lens so that you can refocus it. This is a cheap $5 webcam, and they've calculated an optimal range to focus it at. If you keep unscrewing the lens and get to the infrared filter underneath, and use an X-Acto blade to remove that, or a box cutter, you can see here where the lens fits back in, and with the lens fit back on. There's also a blue LED that turns on when you plug it in, and the updated instructions encourage us to cut that off, so here's Miriam removing it for us to not get in the way of the data. It's said to focus to 9 inches, and so you can see we're using just Skype's preview to test the webcam, and you have to twist it with pliers. It actually helps to heat it up a bit to do the refocusing. Here we are with a sharper image at 9 inches away, which is the focus that's instructed. You then snap the front of the case back on. Then you again want to use box cutters to separate out the layers of the CD. You don't need the opaque side, just the clear side. You gotta cut out a 1/4 inch square, which is surprisingly hard. Takes a lot of scratching. We notched the corner of the square that we managed to cut out to keep track of which edge is towards the edge of the disc, because you have to keep that aligned. It was useful to have a cleaning cloth nearby. This is one for my sunglasses, but we did get smudges on it, and it's good to keep that clean to not mess up the data. We cut a foam adhesive in half, and we use that to put the CDR piece on top of the lens. That's to help split up the light for us. There's a 45-degree piece of poster board that comes with it to situate the camera in the housing at just the right angle to catch the light to produce the results needed. You can see here we're fitting it underneath the flap before we screw the top of the housing back on. And the cord runs out the bottom. It's a simple USB for the webcam. The front of it, there's a good view of the slit at the center of that cardboard thing we initially cut out and folded. There's some weird steps to get Chrome to recognize the right webcam, but the instructions are great on that. Then we pointed it at a light. We were pretty excited to see a rainbow, and we got pitch black. So something was wrong. We weren't sure what yet, but we knew even if we put a bright iPhone LED at the end of it, we still got pitch black. But if we put the bright light right in front of it, we could see some discoloration in the camera, so we knew the cord wasn't wrong. It was sending data. Pry it out with a screwdriver. Maybe it's in the housing wrong. Maybe the light's just not getting to it because it's at the wrong angle. We wedge various junk in there, trying to situate it differently. We keep unscrewing and rescrewing the top of the housing. That's when Jean says, "Hey guys, I think the shutter on the camera is closed." We felt kind of dumb because we looked real close. Yeah, Jean was totally right. Shutter on the camera was closed, and what light we were seeing was just coming through the shutter. And you can see if you look closely here, the disc piece was actually making it hard for us to see that. If the camera is not used right when putting in the housing, you can close the shutter by accident. So we now had to kind of backtrack. We had this shredded up foam adhesive to pry off, and this is Miriam scraping it off with a screwdriver. We needed new adhesive. So I went to the office store, picked up some mounting squares, some Velcro attachments, and some other material, some sticky tack. We really lucked out on the Velcro attachment. It's super strong, but it's sticky on one side, Velcro on the other. And we just put 1/2 on the camera, 1/2 inside the housing. That gave us a lot more freedom to iterate on position and orientation, and we didn't actually even need to use the sticky tack or the mounting squares. Now at that point, we thought we were done with the instructions. We thought it would just work, but we had to spend the next maybe 5 or 6 minutes as a group iterating with lots of fingers, trying to get the orientation of the disc just right in there, to get the line to be perfectly horizontal, because that's what the software is looking for to gather spectrometry data. Yeah.
That's damn close. I don't.
That's just
Well, I think that line wants to be on top of it.
Does it?
We
can move the line.
Oh!
Whoa!
Yeah. So you can see we were pretty excited when we finally got it working. We were again going to get ready to get our first data.
This button.
And then I'm going to line it up with the, oh, shnikes.
Could you bring the lighter also? I'll hold this.
There. You got this on camera?
Yep. Yes.
Wow.
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 Whoa. Cool.
So it took some tinkering, some experimentation, but we did get it working. We all felt pretty good about that. And the instructions, although they were super helpful, we also annotated them as we went. Things maybe if they were explained a little differently, or if some additional notices were mentioned, some additional materials or supplies, how it might have helped us out. And so half the group split off to try to take those notes and improve instructions for future groups doing this kind of project. Gene and I split off to get more spectral data. Here it's from a high-intensity light that I use for recording video. Here's another high-intensity light. This one's a 2500 lumens LED work light. We also use various types of flames. So there's a gas kitchen lighter. Gene did a Yankee candle as well as an iPhone flash, fluorescent light. And all this data is accessible in addition to our documentation on the blog we put together to help document our process, which you'll find the URL for at the end of the video. One last thing that we wanted to do as a group, though, was get together data from colored LEDs because they're bright. They're very specific, sort of what expectation we have. LEDs are very energy efficient, and so maybe a crude hypothesis is that you're going to get a really clear spike and that the area outside of it will be virtually not there. That maybe just made sense to me as kind of mapping to the energy efficiency of them. And so we tried that out with different LEDs in test mode on the pinball machine. And sure enough, that's the result we got. We got orange, red, green, and blue. Pretty clear bands, pretty clear spikes, and white, of course, being the combination of red, green, and blue. And this is partly because I'm obsessed with pinball, but also just to help kind of give us a baseline of something we had some idea of what to expect, and when it produced the image we thought it should. So you should check out our blog. It's got our documentation, our notes, and our memos, as well as links to our actual research results. Thanks for tuning in.